So now I'm going to present some slides on fluvial geomorphology. And rivers do a number of things to the landscape. They erode the landscape at certain points, both in their headwaters as well as along the river channel. They transport material in terms of both suspended material as well as dissolved material. And they're going to deposit material both along the course in these, landforms like point bars as well as in their deltas. And as a result, or one important thing about river deposits is they actually sort their material. So when you look at a river deposit, they'll tend to be stuff that's all around the same size. So these point bars you see often sort of sandy, gravelly size stuff, depending on where you are in the river, whereas the delta will be, the further out you go, the finer the material will tend to be as the velocity of the flow decreases. And this is all explained by a famous diagram known as the Holstrom curve. And this shows the different stream velocities that particles are eroded at, transported at, and deposited at. So let's examine this diagram a bit more closely. So we'll start with deposition, and no surprise, bigger particles will settle out of the flow at a higher velocity. And you only need a little bit of flowing water to carry silt, or even clay particles tend to go right out into the ocean at a delta oftentimes. But it's really easy to knock gravel or bigger particles out of the flow if they even get picked up at all, which is usually only during flood conditions. But what's interesting about this diagram is the eroded part. So you see sand is actually the easiest particle size for streams or river flows to erode, and clay is actually very difficult. And the reason is, well, there's two reasons to it. One, because the silt and clay particles are so small, it's hard for the flow to get under the particles and sort of pick them up, give them that initial burst of energy to get them into the flow. The other thing is that, especially with clay is electrically charged, so it is actually cohesive. It sticks to itself. So this also makes it particularly challenging to erode clay. So it's really easy. It's easiest to erode sand, and it gets actually more difficult to erode smaller than sand as well as larger than sand. But the depositional relationship is a bit more intuitive. The smaller the particle, it'll stay in the flow longer. So once we've entrained our particles and we're transporting them, there's a few different ways that streams can transport material. Firstly is solution, by dissolving stuff. Think like limestone, calcium carbonate rocks that get dissolved. Next is suspension. So oftentimes with silt or clay particles, when you see a river that looks really muddy, the Yellow River is a good example, but many rivers have this. That's because of its suspended load, because it doesn't dissolve the silt or clay, but it's carrying it in its flow. Now, for larger particles, like I'd say sand-sized particles and above in most rivers, they'll actually never really get picked up into the flow. They'll either saltate or they'll bounce along the stream bed, or for really large stuff, they'll either be dragged or rolled by the stream flow in a process known as traction. So now that we've transported our material, we can now deposit it, and there's a couple different places that this happens. Firstly, in the cut bank point bar scenario. So throughout their course, a lot of rivers tend to meander like this. And as we noted with our stream velocity in the last recording, the area of highest flow doesn't want to change direction. So it'll sort of always be on the outside of these curves. You can see when it does this, it's going to be an erosive force. It's going to cut into the bank, forming, well, a cut bank. And you can actually see quite steep bluffs form, in these cut banks over time. Definitely do not build your house over here, but many people do. And on the opposite side, remember we have that low flow, so we'll actually get quite a bit of deposition in the form of these point bars. And the net result of this is that these meanders tend to get larger over time. Now, the other area we tend to get a lot of deposition is deltas at the end of the stream flow. And part of the reason for this, if we think about our continuity of discharge, you have the same Q, same discharge, but it's spread over many different channels or distributaries over a much larger area. So our cross-sectional area is a lot higher in deltas, which means that our flow velocity therefore must be a lot lower. So some of those like silt and clay-sized particles especially start to get deposited. And remember, rivers will sort, so often in a delta like this, I don't have the exact data, but you'll tend to get the more sand-sized stuff at the start of the delta, and as you go out, it'll get finer and finer until you get silt and clay-sized stuff over at the end. But there are various types of deltas that you can find in nature, and it's not just dependent on the rivers, it depends on the relative strength of river flow, wave flow, and tide flow. So with river deltas, you can think about the Mississippi as a fantastic example. You're in the Gulf of Mexico, so the sea is relatively calm there, and you have a really powerful river flow in terms of the Mississippi, so you tend to get like this bird foot delta shape where the river is flowing into the ocean unimpeded. Now, if you go down to tide-dominated, tidal currents tend to flow more perpendicular to the coastline. So it'll rework the deltaic deposits and form these sort of, linear perpendicular features to the coastline. And then the other option here is a wave-dominated delta where once the river drops off the material here, you'll get longshore drift effects, which we'll talk about later in the recording, and you tend to get material move parallel to the shoreline, forming sandbars sort of like this. Now, another thing to think about with river flows on the big scale is this idea of down cutting. And rivers, they're going to want to cut down to a base level, whether it be a local base level like a lake, or eventually, if this lake disappears, it's going to be an ultimate base level like the ocean. And this means that erosion will be concentrated more in the headwaters, generally speaking, and deposition will be concentrated more towards the ocean. This is just how rivers tend to work. So if you have a lake here, or you have like a resistant rock layer like you have with Niagara Falls, or if you build a dam, that'll create a local base level and end up mitigating some of that down cutting. Another thing to talk about with rivers is, of course, this concept of a watershed. So now that we've talked about sort of every part along the river system, we can talk about watersheds or drainage basins. And we can think about them at many different scales, from small scale ones like this creek and Waterloo region, to large scale ones like the watershed for the Hudson's Bay here. Another interesting and useful thing about watersheds is they're what's called a natural integrator. So all of the runoff, the sediment, the nutrients, whatever, that comes from this area of land is going to pass through this point right here where my cursor is. So if you set up a monitoring station there and records your data, then you're going to get a general idea of what's happening throughout this big area of land, which is quite useful. Now, watersheds can have many different drainage patterns, and the ones I showed you there mostly fall into this number one here, which is dendritic. And this is what happens when there's really no geologic constraints on water flow. This is what water tends to do on its own. But more often, maybe not more often than not, this is the most common one, but often on Earth, you'll see geology having an impact on water flow as well. So, for example, if you have, steeply dipping strata and you have more resistant layers here, you can get this trellis type drainage where you have a series of parallel streams and maybe one will cross over every once in a while. You can have radial streams where you have, say, like a mountain or a volcano and stuff's draining off of it. You can have rectangular drainage if you have jointing in your rock. Limestone might be a common one for this, but there's other rocks with jointing as well. Or in areas like the Canadian Shield, where you have a really strong resistant bedrock and it was really recently glaciated, you get what's called a deranged pattern, where you have a ton of lakes and water's still sort of figuring out what to do in terms of draining from that landscape. Another thing to talk about with watersheds is hydrographs and flooding. So all stream channels will have what's called a base flow, which is sort of the minimum amount of water that's usually going through them in the summer months. And this is often from either, residual moisture and rain, but more often than not from contributions from groundwater. And I shouldn't say all streams have this, because all perennial streams in humid climates have this. However, many arid climates have what's called ephemeral streams, where they actually have no flow during the arid times of the year. Wadi would be an example of that. But in addition to the base flow, you can also have this quick flow when you have a large precipitation or a quick snowmelt event. And once you have water inputted into the system, you'll have a certain amount of lag time, but then the water will rise. And understanding these diagrams called hydrographs is a really key for flood management, because understanding how long it's going to take before the flood hits, how high the water is going to be depending on the rain event, and also you can do several best management practices like establishing wetlands to retain the water in the landscape and flatten out this hydrograph so that it's released more gradually. The opposite end is when you pave over a lot of surfaces due to urbanization, and you're going to really decrease this lag time and increase this peak discharge. So that is it for our section on fluvial geomorphology, and next we're going to talk about stream ecosystems.